Hello. So I hope all of you are doing fine. Let's try to understand and practice to find out solution for or balancing a system graphically when a situation is discussed in a problem. So let's see this problem. This being the very first problem is quite simpler in a way. So it is given that there is a shaft having 4 masses attached to it, and here in this problem they all are revolving in the same plane, and the magnitude of masses is given as 6 kg, 5 kg, 9 kg, 7.5 kg respectively. So I can name these masses as M1, M2, M3 and so on, and their CGs are located at a radial distance of whatever these values given from the axis of shaft or axis of rotation, right? It is so first thing will be always to write that data properly, and to get the solution I will always prefer to write that data in a tabular form so that we understand and we are in a better position to draw the vector diagrams. Then the inclination or the phase of all these masses about the axis, they are given with reference to the first mass. So if we read the statement, so angular position of second, third and fourth masses from the first mass are given as 60 degree, 135 degree and 270 degree respectively. So we'll be taking the first mass as the reference mass, right? So what we are here to do is determine the magnitude of the balance mass which is to be put in the system. So that means in this condition the system is not balanced. We are balancing this system by adding one mass in the system, and that mass is at radius 35 centimeter from the center of rotation, right? So let us first take down write those in a tabular form. So maybe this is M1, M2, M3, M4, and there is supposed to be a fifth mass which is a balancing mass. So here I'll name that as MB, right? So these are given. So these values are given to me, so I have tabulated them. So their mass and its corresponding radius of rotation, right? And we know that when this system is rotating at some angular speed, so what is happening in this case is the centrifugal force will be acting on all these masses as they are eccentric, and they will be in different direction. Why? Because their angular phases are given to me. So they are at phases, so at different directions. So the resultant direction, and in the resultant direction of the force there will be this inertia force, unbalanced inertia force, which will be acting, and we have to place a mass which is opposing that unbalance, which will give me the balancing mass. So this is supposed to be the force, so is supposed to be mr omega square. Now we know that when it is all these masses are revolving in the same plane, so there is no question of couple coming into the picture. So it will be only the forces. That means when we satisfy as summation of all these forces to be as 0, our system will be balanced, right? So system will get balanced the moment we ensure that summation of all these forces, including this balancing mass, comes out to be 0. So as they all are mounted on the same shaft, so from the equation omega square can be very well neglected. So we'll be taking only the product as mass and radius. So here if we say our unit will be kg centimeter, as we are dividing every value. So now we'll write all those values here. So this is how we then complete this last column, this product of the first two columns. So we are having these force values with us. Now what we have to ensure here is summation of forces to be 0. So we'll be going for a force polygon, and if I want to satisfy this condition, that means the force polygon must be a closed polygon. Now for that, first I'll have to get the phase diagram. So for this, the angular positions are given to me. So with respect to that, then first we'll go for the phase diagram. So I'll take this M1 as the reference mass. So now in the phase diagram, it is not necessary to draw the exact radius of that mass. What is important in phase diagram is the angular placement of. So I take the horizontal as the reference. We can take as well vertical as the reference. Reference can be anywhere. The only thing we need to care is when we are placing the phases, they should be appropriately placed. Now the first mass is the reference, and M2 is inclined at 60 degrees to M1. So we measure 60 degrees now from M1. So 60 degree from M1 is M2. Then 135 degree. So 90, 10, 100, 10, 20, 130, 135 from M1, and 270. So it is 180. Plus 90 will be 270. So these are the phases. So first is at 60, 135, and 90. So this is M1, M2. Now whether it is mentioned or not, we will be always measuring the angular positions in the same sense, right? So it can be clockwise, counterclockwise, but usually we measure angle counterclockwise. So we will prefer, or I am preferring here to measure all these phase locations as this. Now we are here to determine the phase and mass MB. Its radius is known to us. So now we will go for the force polygon. So we will go for the force polygon, and of course I'll have to take an appropriate scale. So maybe here I'll consider 1 centimeter as somewhere around, looking into the maximum value, I take this as 15 kg centimeter. So when I'm drawing the vectors for these, I'll be following this scale, right? So for that, first we locate the pole. Somewhere here I locate the pole. I'll be moving this, then this, and then coming down to somewhere here. So I'll be requiring more space. So I take this as the pole O. Now, when these are rotating, so the forces or the centrifugal forces due to mass 1 will be acting radially outward. That means in this direction. Force due to this will be acting radially outward. For M3 also it will be acting radially outward. For M4 also. So the vectors will be in the direction of the force acting, and accordingly we will draw. So according to this, if I see My first value is 60, that means according to my scale, so 60 divided by 15, I get the first. So matching with the phase of M1, I draw the first vector. See, I am matching with the first, right? First M1 phase, and I draw the vector. Now as this is moving this way, so I'll move my pencil also in this way. Now this vector comes out to be of 4 centimeters, so I mark this as 4. So this is the first vector, so I name this point as, say, 1. So this value is actually M1R1, this length. Now the second M2 with respect to M1, this vector is in this direction, so I match my roller scale with the phase of M2, roll it at, so I roll it to the pole 1, and I draw the vector first. So it is coming out to be 62.5. So 62.5 divided by 15, it comes out to be 4.16. So 4.2 mm. So 4.2 centimeter. So 4.12. So I get this point as the pole 2. So this is the second vector. Now this is M2 R2. So the third is in phase with this, so I match the roller scale with the third, roll it to the second pole, draw this line. Now this is 135. So 135 divided by 15, so I get it as 9. I'm getting this as 9 centimeter. So I take 9 centimeter. Fine, so I get this vector as this. So this is the third vector. So this is M3 R3, right? And M4 is in this direction, and it is 56.25. So 56.25 divided by 15, I get this to be as 3.75. So 3.8 I can take somewhere centimeters. So 3.8. So this is the fourth vector. So this is M4 R4. So as summation of forces is supposed to be 0, so we will join the last vector with the pole. So the resultant is actually in this direction. So the balancing mass which we are going to put, we will be putting it in this direction. So this is how we join the last vector. So matching with this, when I roll it, so I get the balancing mass position to be as this. So I show it with the pen here. So we get this as the position of the balancing mass, and measuring in the same sense, we will specify its value. So this comes out, this is actually MB35. So the balancing mass from the force polygon, so it comes out to be, if we measure, it is coming out to be 6.1. It is coming out to be somewhere 6.1 centimeter. So this is coming out to be 6.1 centimeter in the scale, right? This, so MB35 is coming out to be 6.1 centimeter as the scale value. So according to our scale, so it into 6.1 into 15. So MB is equal to, this comes out to be 91.5 kg centimeter divided by 35. This is in centimeter. So MB, balancing mass, comes out to be 2.61 kg. So in my case, so there can be a little bit error in the system. Now as I am doing it quite in a crude fashion, so somewhere it is 6.1. Yes, so more or less, so somewhere 2 to 3 kg should be the balancing mass. Now what is remaining is the phase. So what is its phase is, let's see the phase. So for measuring the phase, so it is coming out to be somewhere 270, 275, 76, 77. So the angle is coming out to be, I named this phase angle as theta. So this theta measured from, with reference to mass 1, is coming out to be 277 degrees. So if we place a mass of around 2.6 kg at radius 35 in phase this in the system will be balanced. So that is how we can solve graphically a problem where balancing is required to be done. So that's all in this problem.